everybody and welcome back to another video. In this video, I will be covering directional derivatives from Calculus 3, aka multivariable calculus. So in this question, we are given the function f of x comma y is equal to z, which is equal to x squared plus y squared plus 2xy. Now, we can graph this function in 3 dimensions. I will give an approximate guess of what this looks like because I do not actually know and I don't feel like drawing it too exactly right now. So we have our z, our x, and our y. So this, since it's x squared and a y squared, with this extra term right here, when it's 0, it's going to be 0, and it's going to be in the form of a parabola. So it's going to look something like this, and we'll have some going up, some going backwards, some going over here, and we will have these arcs around here. So our function will look something like this, and it will be just going upwards. Now we are looking for the derivative of this function along a line this way. So we are looking for the partial derivative of this function along the line represented by 2, 1. So for every one movement in the y direction, there is two movements in the x direction. So we are moving in a line which looks like this, and this is the direction of which we are moving in. So this is our direction that we are using for our derivative, and our directional derivative is just the rate of change of this z when looking at this function through this direction. So of course you can start this at any point. So for example, you could be going in this direction at this point, and then you would get a coordinate curve. You would get a graph that looks like this at a given, and then this would be z, and then this would be your x comma y, but like a given x comma y direction. So you could just write this as a new variable. Let's just say that this is t, or v, I guess makes more sense, as that is our direction that is commonly used. And this will look like that, it can look like this, it could look like that, it could look like this. This is just a coordinate curve, and we are looking for the rate of change of this coordinate curve, or the derivative of this, the tangent line approximation, not approximation, it would be exact in this case, at any given point. So, let's go over how to do that. First off, we need to know about gradients. Now, the gradient of a function f, which, let's say, f maps from R2 to R. So an example of this is f of x comma y is equal to z, which is what we are dealing with. The gradient of f is equal to the partial derivative of f with respect to x, comma, the partial derivative of f with respect to y. So this is our general gradient formula, where the partial derivative is just that idea where we talked about. However, it is along the direction of y and along the direction of x. So the partial derivative with respect to x would be the rate of change of this x coordinate curve. So this would be x and z, where if you vary y, it will in fact change it. So if you're closer, it will be higher up. And if you're in the middle, it'll be down. And if you're farther, it will also be higher up. So it will look something like this, and given on your x and y, given on your certain x values and your certain y values, you will get a tangent line, which represents your partial derivative at that value x comma y. And same thing applies for y. I think you understand the point by now. So this is just a vector that represents the changes in both x and y. So now if we do the dot product between the gradient of f and our vector, we will get the directional derivative in that direction. However, we want the length of our vector to be 1, as we want this to be a unit change of 1 in this direction that corresponds to a given unit change of z in that direction. So we will do v over the magnitude of v. And this is our formula for our partial derivative of f over a vector v. So now, let's get to plugging this in. So since we treat x as a constant for the y partial derivative, since there's no y here, and y is a constant for the x partial derivative, then we can do the following. So df over dx, the partial derivative, is equal to, the x just becomes 2x, then this y, it's a constant. Imagine that's just like 5 or something. So that just becomes plus 0, so I won't write that, as the derivative of a constant is 0. And then the derivative of 2xy with respect to x is going to be plus 2 times y, since y is also just a constant. So df over dx is equal to 2x plus 2y. Now, also I'm going to rewrite this as x comma y, and this is x comma y, and this is just our vector. So our partial derivative of f with respect to x is 2x plus 2y. Now, our partial derivative of f with respect to y is equal to, this is just a constant, so 0, plus 2y, now plus 2, since this just drops down to 0, plus 2x. So as you can see, these are actually mirror images of each other where you just flip the x and the y's. So these are actually the same. Now, our gradient of this function, so we are looking for the directional derivative in the direction of x comma y is equal to 2 comma 1. So let's just write our gradient out first. So our gradient of f is equal to, this would be 2x plus y, 2y, sorry, comma 2y plus 2x. So this is our gradient of our function right there. Now we want to find our unit vector, which the direction we are moving. So let's call that u, which is equal to v over the magnitude of v, such that just v is equal to, the length of v is equal to 1, which is u. So u is equal to our vector v, which is 2 comma 1, that is the direction in which we are going, you can see it right here, divided by our length function, which is just the Pythagorean theorem for this, as if you move this way and you move this way, then the length that you move, or I guess if you move this way and then you move this way, then the length that you move is just going to be the square root of x squared plus y squared. So x squared plus y squared, this is just over the square root of 5. So this is our u, which is equal to v over magnitude of v. Now we can just plug this in and do our dot product. So we get that the partial derivative of f over the partial derivative of v in the the derivative of f in the direction of v is equal to 2x plus 2y comma 2y plus 2x dot our magnitude vector, which is going to be 1 over radical 5, as we could just pull that out, times, so this is a dot product right here, times 2 comma 1. Now for a dot product, we just multiply the x components and the y components and add them together. So I will move this outside over here on the general. So let's just actually put this over here, since this is a multiplication. So then we get df over dv is equal to 2x plus 2y times 2 is 4x plus 4y. And now 2y plus 2x times 1 is just plus 2x plus 2y. And this simplifies to, oh wait, and then we have to multiply the 1 over radical 5. Sorry, I forgot to bring that down. Now this just simplifies to df over dv is equal to 4x plus 2x is 6x. Then 4y plus 2y is just 6y. And these are both over the square root of 5. And this is our answer. So this is our partial derivative function in the direction of v, where v is 2 comma 1. So I hope you all enjoyed this video, learned a lot. This is a very interesting topic, and you need both gradient and length vectors in order to solve this problem, so I think it is a very good problem for getting the gist of differential multivariable calculus. So anyway, I hope you enjoyed this video, and thank you for watching.